Hello, everybody. Welcome back. We're looking at Chapter 2, Section 4 today. Section 4 deals with symmetry. What exactly is, when something is symmetric, what does that mean? For example, if we had a mirror, just that was a mirror, and if we drew a line this way, the symmetric, it'd be a mirror image. Symmetry is a mirror image. Now, in our XY graph, let's say we had a point here at 3, 1. We're going to look at not only just if something is symmetric, we're going to look at what are called the reflections. So if it's symmetric, it has a mirror image. A reflection is just that. It's about one of three axes. Reflection about the x-axis. That means whatever's here will be here. There's a reflection about the y-axis. Means if I have a point there, there's a mirror image right there. And the last one is about the origin. So we have a point there, then it's about the origin there. So let's look what's happening here. If something has a reflection about the x-axis, we'll look at this point here. If it's at 3, 1, about the x-axis, we'll put it at 3, -1. So if something's reflected about the x-axis, the x value stays the same. The y value changes signs. All right, so if it's symmetric with the x-axis, or if it's a reflection about the x-axis, then all we do is change the y values. It's a reflection about the y-axis. Then we have this point here, which is -3, 1. It's reflexive about 3, 1. So if it's reflexive about the x-axis or the y-axis, the x values stay the same. The y value stays the same, it's on the same horizontal shift, and the x's change from positive to negative. X value changes sign. Now, if it's across the origin, this is, let's say 3, 1 here. So now this is going to be -3, -1. Both x and y values change signs. Okay, so that's what it means to be reflective. Because once it's reflective, then we have a symmetry. It's equal on both sides of the axis it's looking at. we do the same thing. We have reflection of graphs, not only just single points, but we look at all the points. For example, let's look at the line y equals 3x plus 2. If we drew the graph, it crosses the y-axis at 2. So we have a dot there. The slope is up 3 over 1. So 1, 2, 3 over 1. We have another dot there. So it's at 3, 4, I said 5, 1. So then again, slope, go up 3, 6, 7, 8. We add 1, so it's 2. So it goes from 0, 2 to 1, 5 to 2, 8. So now, what if we want to flip this line across the x-axis? We want to flip it this way. So to flip it across the x-axis, what stays the same? If we're going to flip across the x-axis, the x values stay the same. Y goes from positive to negative, and the x value stays the same. So what I would do here, I would still have the 2, but now it would be a negative 8. So it'd be 2, negative 8. Then it'd be 1, negative 5. Just 2, negative 8. And then the second point is at 1, negative 5. At 2, 0, 2, leave the x alone at 0. It would be at negative 2 now. And there's our graph. So these two graphs are the same. It's just that they're flipped over the x-axis. All we do is just reflect about the x-axis. Just change the sign of the y values. So that's what we do if we want to flip across the x-axis. Let's look at the equation. And reflect it about the y-axis. The original equation, okay, it started off at 2. And we'll go up 3 over 1, up 3 over 1. So we have our points at 0, 2, 1, 5, 2, 8. So to flip across the y-axis, so the y values stay the same, x changes from positive x to negative x. So that's what we have to do. So to change the sign of x. So this new point would be negative 2, 8. Negative 1, 5. 0, 2. So there's the reflection line. So we start off at 2, 8. To flip across the y-axis, we just change the x value. And that flips across the y-axis. Let's look at the same equation where we reflect about the origin. Remember, if it's the origin, x goes from positive x to negative x, y goes from positive y to negative y. So we flip across both the x and the y-axis to get to the origin. Let's flip down and across, flip over it and down, so it doesn't matter. So graphically, here's our original equation. It's at 0, 2, 1, 5, 2, 8. So to flip across the origin, I have to now change the signs of both of these. I have to go to negative 2, negative 2, negative 8. Then the next point, 1, 5 becomes negative 1, negative 5. And the last one is 0, negative 2. So there we have the reflection line. They're going to be parallel. And they both cross. One's at negative 2, one's at positive 2. All right, so that's how we look at reflections about the x-axis, y-axis, and origin. Now, you'll hear talk of odd, even, or neither. Basically, a function can be odd, even, or neither. Let's look at even first. The basic rule for even function is this. You have a function, I don't care what it is, it could be anything. What the test is here to test if it's an even function. If you change the x value from positive x to negative x, it doesn't change the function. So that's an even function. In other words, it stays the same. For example, x squared plus 4. The way you test to see if it's an even function, we have this function. Let's put a value in there too. So 2 squared plus 4 4 plus 4 equals 8. So when x is 2, y is 8. That's a point. So let's do the same thing again now, but this time let's put the negative of that value. So this is positive 2. Next one, we're going to put in negative 2. We put negative 2 in place of x, so it's negative 2 squared. Negative 2 squared is 4. So that's an even function. So it doesn't matter if I plug in a positive or negative, I still get the same answer. What does that look like? What changes here? Only the x values. So if it changes only the x values, it's reflexive about the y-axis. So even functions are reflexive about the y-axis. Because we change the sign of x and the sign of y remains the same. So if you have an even function, then it's reflexive about the y-axis. And we're going to have examples, so we just look at it and you tell me if it's odd or even, or neither. Let's look at even. No, that's odd. Let's look at odd. Let's look at odd functions. An odd function let's look at x cubed. What an odd function says, if I change x to negative x, that will give me an answer that will be the same as the negative of the original. So what's happening here? We know what f of x is that, so it's so we're changing x to negative x, and y is going from positive to negative. So y is also changing signs. So an odd function, when x changes from positive to negative, it changes the answer from positive to negative, or just changes the sign of the answer. This is reflexive about the origin. So if a function is a reflexive about the origin, then we know it's an odd function. If it's reflexive about the y-axis, then we know it's an even function. So basically, you're not supposed to reflect about the x-axis. Because if you reflect across about the x-axis, let's say we had that function. If we reflect it across there, we no longer have a function because it fails the vertical line test. It will fail the vertical line test. Remember, the vertical line test says if it's a function, you have to be able to cross it vertically only once. Yeah, so we only have for odd, even. Anything else is neither. Let's look at an example of a neither. F of x equals, this is for a neither. So if we plug in 2 inside here. So we have 2 to the third plus 1. 2 to the third is 8. 2 times 2 times 2 plus 1 is 9. What happens if we put in a negative 2 inside there? So negative 2 cubed plus 1. Negative 2, negative 2, negative 2, negative 2 has 3 negatives. So the answer is negative. 2 times 2 times 2 is 8. Plus 1 is negative 7. So when x changes from positive to negative, y didn't, you can't even say anything about the y's. So that's what a neither is. Let's look at some examples. Because we have to look at some possibilities with coefficients, exponents, and constants numbers. Each one of those will give us a different possibility. So let's see. Let's look at even exponents. Let's look at the exponents first. If we have an even exponent, what is that? So we have a positive 2, plug that in there. 2 squared equals 4. If we put a negative 2 in there, negative 2 squared is also 4. So x changed from positive to negative, the answer stayed the same. So this is an even function because it's reflexive about the y-axis. Okay, so let's look at what happens. Does anything happen if I put a coefficient in front of the function? And even exponents. I'm going to do 3 this time. 2 times 3 squared. 3 squared is 9. 2 times 9 is 18. I'm going to do the same thing now with negative 3. So all I do, whatever I put in there, I put the same number in, but different signs. And look what happens to the answer. 2 times negative 3 squared. So 2 times negative 3 times negative 3 is positive 9. 2 times 9 is 18. So x changed from positive to negative, answer stays the same, so it's an even function. So we know that if it has an even exponent, it's an even function. If it has an even exponent and a coefficient, it's still an even function. What happens if we have an even function and we add something to it? Will the answer change? Let's put 3 in there. So it's 3 squared plus 1. 3 squared is 9, plus 1 equals 10. So when x is 3, y is 10. What happens if we put a negative 3 in there? Negative 3 squared plus 1. Negative 3 times negative 3 is positive 9. 9 plus 1 is 10. So x changes from positive to negative. Answers stay the same, therefore it's even. So if the only exponents you have in your equation are even exponents, 2, 4, 6, 8, 10, 12, it doesn't matter if you have a coefficient or a constant added, subtracted to it, it'll always be an even. Okay, let's look at odd exponent. So we have 2 to the third. 2 times 2 times 2 is 8. If I put a negative 2 in there, negative, negative, negative makes it a negative. 2 times 2 times 2 is negative 8. So x changes from positive to negative. Y changes from positive to negative. So it's across the origin. It's symmetric about the origin. Let's see if we put a coefficient in front, if that changes anything. We'll put 2 in there. So 2 cubed. 2 cubed is 8. So 2 times 8 is 16. And the next one is a negative. So change x from positive to negative x, see what happens. So 2 times negative 2 cubed. Negative 2 cubed is negative 8, which makes it a negative 16. So x changed from positive to negative, the answer changed from positive to negative. So because of that, it's symmetric about the origin. Let's see about a constant. When x is 2. So 2 cubed plus 1. 2 cubed is 8, plus 1 is 9. Okay, so when we have positive 2, we get 9. What happens if we get a negative 2? Just change the input. So you have negative 2 cubed plus 1. Negative 2 cubed is negative 8, plus 1 is negative 7. You change the answers, it's neither. Okay, the only last test that we have left to do, because we've looked at even exponents with coefficients and with constants. So it doesn't matter, anytime you have only even exponents in your equation, it'll always be even. If you have odd exponents, 3, 5, 7, 9, then it's going through the origin. If you have a coefficient, also go through the origin. But odd exponents cannot be matched up with constants. If you do that, it's a neither. You can only add and subtract numbers to an even exponent. The last thing we could look at is, let's see what happens when we combine odd and even exponents. Okay, so first off, it's positive 2 when put in there. So we have 2 cubed plus 2 squared. 2 cubed is 8. 2 squared is 4. 8 plus 4 is 12. So if x is an even 2, we get a positive. If x is a positive 2, we get a positive answer. Let's put a negative 2 inside there. Negative 2 cubed plus negative 2 squared. Remember, we're testing it if we have different exponents. Negative 2 cubed, negative, negative, negative makes a negative. 2 times 2 times 2 is 8. Negative 2 squared is 4. 8 is bigger than 4, it's negative. 8 minus 4 is 4. So to determine if a function is odd, even, or neither, that's what we have over here. So if the only exponent you have in your equation, now you can have 7 exponents, but if they're all even integers, it is an even function. If you have an even function, a squared exponent, and a coefficient, it doesn't change it. And if you have an even exponent and you're adding and subtracting a constant, it doesn't change it. So if you have only even exponents on your x's, no matter what, it's always going to be even. The only time an even exponent will not be even is if you mix it up with an odd exponent. The power, this is a 3, that's a 2. Because you're combining different exponents, it's neither. And if you have an odd exponent, you can have just a function x itself, or if you have a coefficient, they're both going to be symmetric about the origin. But odd exponents cannot match with constants. If you do that, then you get a neither. So with that, we just take a look at an equation now. Is this function odd, even, or neither? Well, we could just look at it. Look at the exponents. That's odd. That one's odd. And this one is, since there's nothing there, it's actually a 1. It's also an odd. They're all odd, so this is an odd function. Since it's an odd function, it's reflexive about the origin. How about this one? All of the exponents, all the x's you have are even exponents, and there's no constant. Likewise, up here, there's no constant. This is no constant, and they're all even. We know this is an even function. It's reflexive about the y-axis. We showed it the way we test it. Let's test it with 1. 1 to the power 8 minus 3 times 1 to the power 6 plus 4 times 1 to the 4th, 2 times 1 to the 2nd. 1 to the power 8th is 1. 1 to the power 6 is 1. Times 3 is 3. It's a minus 3. Plus 1 to the 4th power is 1. 1 times 4 is 4. 1 to, so it's times 2. 1 minus 3 is negative 2. The 2's cancel, so it equals 4. That's what it is with positive 1. Let's look what it looks like at negative 1. So we have negative 1 to the 8th, negative 1 to the 6th, negative 1 to the 4th, plus 2, negative 1 squared. Anything to an even exponent becomes positive because they're always in pairs. So this is a 1. Negative 1 to the 6 is also positive 1. Negative 1 to the 4 is 1. Negative 1 squared is 1. 3 times 1 is 3. 4 times 1 is 4. 2 times 1 is 2. 1 minus 3, 3 is bigger, so it's negative 2. 2 and negative 2 cancel out, equals 4. So since we went from positive 1 and we got a 4, then we went to negative 1 and we also got a 4. The x's went from positive to negative, but the y's stayed the same. That's even. So another one. Okay, look at the exponents. There's an odd exponent, there's an even exponent, and a constant. Because of that, I know it's a neither. I know it's neither because first off, odds and evens can't go together, and odds cannot have a constant. So let's try it. Let's do it negative 1 and 1. So we have 2, 1 to the power 3, 3, 1 to the power 2 plus 1. 1 to the power 3 is 1. 3 to the power 2 is 1. 2 times 1 is 2. 3 times 1 is 3. 2 plus 3 is 5 plus 1 is 6. So when x is positive 1, the answer is positive 6. Let's try it with negative 1. 2 negative 1 cubed plus 3 negative 1 squared plus 1. So we'll look at the first one. Negative 1 times negative 1 times negative 1. The answer should be negative. 1 times 1 times 1 is 1. Negative times negative is positive. 1 times 1 is 1. And positive times negative is negative. 1 times 2 is 2. So it's negative 2. Positive, positive is positive. 3 times 1 is 3. It's 1. Negative 2 plus 3 is 1. 1 plus 1 is 2. They're not equal, so it's neither. So you see, if you just go by the rules, if you have an odd exponent, all of the exponents have to be odd with no constant number. Then you have an odd function. That's symmetric about the origin. If you have only even integers, or only even integers with a constant, then you have an even function. That's symmetric about the y-axis. The problem comes when you start mixing exponents, odds and evens, neither. Odds with a constant, neither. So that's a shortcut. All right, that does it for section 4. Now, section 5 is where it starts getting even more fun. Section 5 deals with what are called transformations. Transformations are just that, they're changes. Changes to the positioning of the graph, the shape of the graph, of any type of functions. We have certain types. We have horizontal shifts. That's left and right. We have vertical shifts. That's up and down. We have what are called also reflections. Reflections is the flip of the entire function. So in other words, if we had a parabola and it opens like that going up, the reflection of it is it's going down. So I take this entire picture and flip it over the over the x-axis. We have horizontal and vertical shifts. We have horizontal shrinks. That's where it pushes together. We have horizontal stretch. That's where we take the graph and pull it apart. And we have vertical shrink, which pushes the graph shorter. And then we have a vertical stretch. That's where it pulls the graph apart, makes it taller, it's skinnier. So that's everything this last section's about. So every function, I don't care what it is, every function has the same basic shape. There it is. A, B, C, and D. Each one does its own purpose. For example, the easiest one is D. D is the constant. This is the vertical shift of the graph. If positive, you go up. If negative, you go down. Whenever you do a transformation, always start off with the basic function. The basic function of this is the y and the x with the highest exponent. That's the basic shape of the curve. Forget everything else. What does x squared look like? Well, we talked about it last class. It's the parabola. That's x squared. Since nothing else happens here, the next thing we could do is when x is 0, well, in the first part, when x is 0, y is 0. It's right there. But now, the shift, when x is 0, y is 2. So this new shift, new graph, it takes the entire graph and it goes up 2 spaces. That's what that says. So all you have to do is figure out what the graph looks like from the library of functions. Then we have it. Let's look at another one. Okay, first thing, here are the steps. Transformation steps. Transformation steps. The first thing you have to do is identify the shape of the function. By shape, I mean the original graph. The original graph. Okay, at this point, you just look at the highest operation, the highest special operation. It's, what does that graph look like? Well, remember from our library of functions, the cube root function looks like this. Since it's odd root, it can be positive or negative. So that's the, now, since this constant is there, that's my vertical shift. When x is 0, y is 0, minus 3, what it does, it lowers it. It lowers the entire graph 3 spaces. So from here, I drop down to 3 spaces. 1, 2, 3. The graph will look the same. There's my new graph. This is the original graph, but this is my transformation. All it does is take this graph and go down 3 spaces. That's all it tells us. So that's your vertical shift. If this is positive, you go up. If it's negative, you go down that many spaces. So draw your graph first, and then whatever it is, then you augment it either up or down. Let's look at horizontal shifts. Horizontal shifts happen inside the function. It's inside the function. It's x plus or minus some number. So for example, the absolute value. So the first thing I have to do is ID the function. Absolute value of x, the graph of it is the v. Next step, follow the horizontal shift. Now remember, the horizontal shift is always inside the function. The function here is absolute values, so this tells me my horizontal shift. Take what's inside the function, set it equal to 0, and solve. So I have to take what's inside the function, x minus 2, set it equal to 0, and solve. That number, that is your horizontal shift. So the first step, we know the function is an absolute value. So that graph is the v. Then I know that there's a change inside here. When I set it equal to 0, I get x equals 2. Now, this is my new shift. What the shift is, it takes the origin where you start off, it moves it. This one says I move it to the right 2 spaces. So my new origin is there, and the graph is still a v. So that's all the transformation is. It's moving the origin from 0, 0 to, in this case, since we're only moving it horizontally, moving it to 2, x equals 2, 0 on the y-axis. How about this one? We identified the function is 1 over x squared. So that's where the x is on the bottom, and it's squared. So it's 1 over, what does the graph of the 1 over x squared look like? The Atari symbol. So that's the first thing I did. I like that. F of x equals 1 over x squared. That's my graph. Then I notice that I have a horizontal shift. There's a plus or minus inside the function, inside the square term. So x plus 3 equals 0. X equals negative 3. So what this tells me is I have to take my graph and move it to the right or to the left 3 spaces. 1, 2, 3. Because remember, what this number says, where it used to be 0, 0, it moved from here 3 spaces to the left, and there's my new origin. So the graph looks the same, but moved over to the left. And that's all there is to it. So you look at the horizontal, you look at the vertical shifts. Notice the horizontal shift, like we talked about in chapter 1, the horizontal shift is always going to be opposite the sign inside the function. So that's x minus 2. The answer is positive 2. X plus 3, the answer is negative 3 because it's opposite of what that is. And that tells us where our x values are going to go. So let's put those first two together. Let's look at the graph of this one. Steps. ID the function. This function is f(x) equals x squared. No, x cubed, I'm sorry. Because the x is inside the parentheses and it's cubed, so it's x cubed. Forget, take away all the other ancillary numbers. Whatever you're left with is the original function. So what is 1 over 1? What does x cubed look like? Well, x cubed, the function x cubed, looks like this. Let's cube it. It goes the other direction. That's x cubed. Second, find the horizontal shift. We know we have a horizontal shift because inside the parentheses affecting x, that's your horizontal shift. This means we move it to positive 2, which is to the right 2 spaces. 1, 2. So that's my new origin. The graph now goes through there. That's a horizontal. And let's look at a vertical shift. Find the vertical shift. Remember, the vertical shift is any constant number outside the function. And negative 3 is my vertical shift. So negative 3 says I have to go down 3 spaces. So I go over the 2, and I go down to 3 spaces. So I take that this point that's there, I go down 3 spaces. So there's my new origin right there. My origin changed from there, from the origin from middle, it moved there. Then it moved from there down there. So this is my new XY axis. The graph looks the same. But we haven't done anything about shifting the size of it. All right. So remember, our function originally looked like this. This y equals. Our equation looks like this. So far, we've talked about these two values. Inside the function, wherever you have the x, if you have to add or subtract something to x before you do anything, that is your horizontal shift. Now, outside the function, with a plus or minus in front of it, that constant number as your vertical shift. You know that's where it goes up or down. Okay, now we have A and B to worry about. Let's look at A. A does a couple of things. If A is negative, the graph flips across the x-axis. If it's positive, it stays the same. So first thing it does, it tells us the direction. So A tells us the direction. If it's positive, it opens up. If it's negative, it opens down. And I'll show you what opens up and down means. We know C is a horizontal, D is a vertical. Now, A also affects the shape of the function. If A is greater than 1, the graph stretches up, upwards and downwards. It's like a silly spring. If you hold it, you just pull it top and bottom and make it into a big oval. So in other words, if it's greater than 1, if the leading term is greater than 1, that means this number grows a lot faster. If A is between 0 and 1, I should say the absolute value of A, because the same thing happens if it's positive or negative. So if A is a fraction, the graph constricts or squishes down. Now, what does that mean? Let's pretend we had the regular function is x squared. This is x squared. If we had 2x squared, it would grow twice as fast. The number in front, that's A. If we had 1/2 x squared, if it's a fraction, then the graph would grow half as fast. So here's our original function. If we have an integer greater than 1, then it becomes skinnier. It pushes the walls in. If it's a fraction between 0 and 1, it pushes the walls out, makes it grow slower. That's what A does for us. It tells us the shape, whether it's going to be skinny or fat, and tells us the direction. Let's work on these before we do the horizontal and vertical constrictions and shrinks and expansions. there. Just by looking at it, what can you tell me? Remember, it's a f of bx plus c plus d. So what's c? C is our function is the absolute value. Inside the function, c is the horizontal shift. D is the vertical shift of the entire graph, not just that one number. And A is the direction and shape. Let's look at this. Let's do it piece by piece by piece. So first step. What's the original function in our equation? Since the function is absolute value of x. We start off with that because we have to know what the graph will look like. That's the original one. We do inside the parenthesis. This is the horizontal shift. Remember, take whatever's inside the function, set it equals 0, and work it out. Offset, remember, it's always going to be the opposite, like the circles. So we know our graph shifts to the left 2 spaces. So at -2, that's my origin shifted from there to there. So the graph still looks the same. Nothing's happened to the graph. Okay, order of operations. Let's look at we have the coefficient. We have 3x plus 2. So that's graph there. Now, what does 3 tell us? It tells us 2 things. 3 is greater than 0. So the graph remains that direction. If it was negative, it would go down the other direction. And then because it's 3, the graph grows 3 times as fast. Okay, so the original function here, if we look at the chart, when x is 1, absolute value of 1 is 1. When x is -1, it's 1. When x is 0, it's 0. When x is 2, when x is -2, and 2. But now, our graph changes. So originally, when x was 1, used to be 1, but now it's 3. So instead of over 1, up 1, it's over 1, up 3. Left 1, up 3. So now this graph is a lot more steep. It's 3 times, it grows 3 times as fast. And the last part, we did these first 2. The last part is the vertical shift. We know it's over 2. And now down 1. So that is where my new origin is going to be. My origin shifted 2 to the left and 1 down. So there's my new origin. That's my new graph. 1, 1, 2. Okay, the graph still is the same. Is that we go over 1, up 3, over 1, up 3. If you can't see it, you have to plot some points. So after you see the graph, you have to plot the points to get the accurate graph, because it's going to ask you to plot a couple of points. Let's look at another one. Okay, let's look at this one. -1 over x minus 2. So first step, what's the function? Since x is on the bottom, no exponent, so it's 1 over x. And we look at our library of functions. 1 over x looks like this. Because when x is negative, y is going to be negative. So the bigger x becomes, the smaller y is. And conversely, the smaller x becomes, the bigger y is, because it's a fraction. All right, so let's look at the first thing. Well, we could look at this. That is our a value, because this equation here could look like -1 x minus 2 plus 3. So this is our a. A is -1. Now, what that does, since it changes the whole answer to negative, means all my negative answers are now positive, and all my positive answers are now negative. This makes it flip across the x-axis. Okay. And we have x minus 2 on the bottom. So we took care of the basic structure. Negative makes the graph flip. This part has to go up there. This part has to go down there. Now we do the horizontal shift. We know it's going to be 2, but I'm going to set the inside equals 0. So we know it shifts to the right 2 spaces. So that means we take the origin, shift it to the right 2 spaces. The graph remains the same, but it's shifted to the right 2 spaces. So we did -1, we just have this +3 now to do. -1 over x minus 2 plus 3. Since we already have the graph of this, all we have to do is raise it up 3 spaces. So there's 2. So we'll raise it up 1, 2, 3. So what used to be here, now I have to go up 3 spaces. Now it's shifted up to here. There's my new origin. And the function, the graph looks the same. There's our answer. All right. Let's see. What we have left to do is the horizontal and vertical stretch and shrink. And they're opposites of each other. So actually, I'll hold off on that till Monday so that y'all get used to doing this. So, and we will finish horizontal and vertical shrink and stretch Monday. All right. Okay, good luck, everybody. And if you have any questions, don't forget to call.